guys, Sir Majesty took away my fear I had in chemistry and biology. You have to join the easy world. My name is Victor Modia, a student in Italy. Anywhere you are, you can join us. Join the easy world. Be a subscriber. Bye. Thank me later. Whenever you reach for me.
You're welcome to Sir Majesty Easy World Science channel. Please don't forget to subscribe and share this video. Please. Okay, for us to move on, here we are going to handle alternative to practical titration question. Remember, in the alternative, you are not going to be provided with any acid or any burette or pipette to do the titration. Rather, you'll be given a question like you can see on the screen. You'll be given the information that you will get from titration, and the information you get from titration is the end point. And then they will mention the reactants. So, looking at this is a guide to help you answer other subsequent alternative to practical questions in titration. They said A is 0.100 mole GM cube, that's mole per dm cube acidified potassium tetraoxomanganate 7 solution. That's a standard solution. Remember, in titration, at least one solution must be standard. Then, solution B is a solution of an iron tablet in which 10.0 gram of the iron tablet was dissolved in distilled water and made up to the mark in 250 cm3 volumetric flask. 25.0 cm3 of B required 17.5 cm3 of A for complete reaction. They gave us the equation of the reaction, which is the ionic equation of the redox reaction, of course. This is a redox reaction because you have the oxidizing agent and here the reducing agent. Manganese 7, potassium manganate 7 should be the oxidizing agent. The iron 2 is the reducing agent, which obviously became iron 3 here. So the species that is oxidized is automatically the reducing agent. It is plus 2 here and now become oxidized to plus 3. So this is the reducing agent. While this species, which is manganese 7, became manganese 2 here. So that's the oxidizing agent. The species that is reduced is the oxidizing agent, while the species that is oxidized is the reducing agent. So here is the oxidizing agent because over here is plus 7 for M, and that's manganese is plus 7 here. But over here is obvious is plus 2. It is written clearly on top, plus 2. Okay, so that is how to know the species oxidized and the species reduced. The one that its oxidation state decreased from left to right, you call it the oxidizing agent. From plus 7 to plus 2, 7 decreased to 2, so that particular species is the oxidizing. Then the species that the oxidation number increased from left to right, from plus 2 to plus 3, should be the reducing agent. And the titration between these species is called redox titration, or rather redox reaction. Okay, now following up to this, what you are required to know basically that you should not joke with is those informations provided. This is A, and A, I told you, is a standard solution. Reason is because the concentration is accurately known. It was accurately mentioned to be 0.1 mole per dm cube. Then in B is also a standard solution, but because of the fact that they did not mention the formula of the iron tablet, remember the common compound used for iron tablet is actually iron 2 sulfate. Iron 2 compounds, ferrous compounds are the common compounds used as iron 2, used in iron tablet. So even in blood tonic, iron 2 tetrodosulfate, even ferrous gluconate, most of them succinate, different forms, but it must be iron 2 compound. Okay, now it was not given totally as a standard solution, so you have to see this 10.0 gram was dissolved in what volume? 250 cm cube. So this is where our interest lies. These informations given, we will be using them as we calculate down. Okay, so don't joke with them that A is this, don't forget it, that B is this, don't forget it, because when we go down, we will use it. The same thing is applicable to any other alternative to practical question. Remember, don't forget to subscribe and share this video. Please don't forget to subscribe to my channel. Please. Now let's see. Number 1 says, from the information provided, calculate the I number of moles of manganese 7 ion, that's MnO4 minus, in the volume used for complete reaction. The volume used for complete reaction, you see the grammar here, for complete reaction. And what's the volume of manganese used for complete reaction? 17.5. So that is our interest, and they have already told us that KMnO4 have this strength. Now, to give you a secret, what we're going to do is definitely we have to interpret this concentration. What does it mean? This 0.100 mole per dm cube, what does it mean? It means that, remember that 1 dm cube is equal to 1000 cm cube. And what does this imply? Implies that one can write 0.100 mole per 1000 cm cube. Replacing the dm cube with what? Cm cube is the same thing. When we say 2 per room, it means that 2 people are contained in a room. So to interpret this, it means that 1000 cm cube contains 0.10. Then in the 1000 cm cube that contains 0.100, 17.5 was the volume that was used. That's what we see as our VA here, or the end point. They gave it to you. While this is the volume of the pipette you used, of course, that's the B. Now, 17.5 is the volume used out of this whole 1000. So if 1000 contains 0.100, what will 17.5 cm cube contain? That is going to be our answer. So you cross multiply such that we now have 1000x is equal to 0.1. Remember, 0.100 is the same thing as 0.1. The 0 after point is not counting unless there is a significant figure following that 0. Okay, so 0.1 times 17.5, which will take us to find out that x is equal to 0.1 times 17.5. Divide both sides by 1000, which is the coefficient of x. This is what we have as, this is what going to be our final answer. So we try to use the calculator to check our final answer. From what we have, we are multiplying 0.1 times 0 times 17.5, of course. Then finally divide by 1000, which will give you 0.00175. If I correct, yeah, 0.00175. This will give us 0.00175 what? Moles of MnO4 minus. Now, to clear the air more for you, remember they said that A is KMnO4, but the question here said MnO4 minus. So the only secret there is that A is given as KMnO4. So dissociate this into its constituent ions, K plus MnO4 minus, and the equation is balanced. That means that 1 mole of this will also give us 1 mole of K and 1 mole of MnO4. So this implies that whatever mole, this automatically implies that whatever mole of KMnO4 you get is equivalent to the mole of manganese 7 ion. So the same mole we get here is also for the manganese 7 ion and also for this. Now, take for instance, see what I mean here for you to understand further. Let's assume that the formula for KMnO4 is, I say let's assume because this thing doesn't actually, let's assume this is KMnO4. This one is potassium tetraoxomanganese 6. If you are dissociating this, it means 2K plus MnO4 minus. This one means that 1 mole of K2MnO4 will always give you 2 moles of potassium, and the same thing as 1 mole of this. But let's assume the formula of A is K bracket MnO4. Let's assume this compound doesn't exist, bracket 2. You dissociate it, it will now be K plus 2 MnO4 minus. Let's assume this is our own case. This is the case of the compound they gave to us. In this case, assume is what we are saying. If we are given this type of thing, K bracket MnO4, there won't be minus inside it, please. Bracket 2, this compound doesn't exist. But let's assume they gave it to us. Now, this implies that 1 mole of the compound, which is A, will give us 1 mole of potassium and 2 moles of MnO4. Let's assume this was the situation of A. It means that this answer I got here, 0.00175, should be for this particular one. And following the mole ratio, 1 mole of this will always give us 2 mole of this. So let's assume this is our B, the formula for our A. I will now have to times this by 2. But unfortunately, the formula of A is this one here. So this particular formula you are seeing here, the KMnO4, which will give you 1 mole of this particular manganese 7 ion. So 1:1, therefore 0.00175 is also to 0.00175. So this should be our correct final answer. But let's assume on dissociation we get 1:2. We have to multiply by 2. That's it. Okay. Now let's move on. Let's clean these ones that are not necessary.
Hi, I wanted to tell you that you can contact Majesty for your laboratory equipment and reagents. They are affordable and provide accurate results too. Majesty's word only sells what he knows, and his patterns of delivery are sure and certain. Place your orders today. Thanks for your patronage.
Using my prepared filler, you can also place order for any of these apparatus and reagent to Majesty.
So this is automatically our final answer for question I. Then we move on to question II. Says number of moles of ion 2 ion in 25 cm cube of B. Is the same thing that we solve here. The number of moles. Then you go back to the information given. The information about B says that B is 25. That B is actually containing 10 grams in 250. They didn't give us the molar mass of B, and therefore we cannot interpret this 10 grams, this mass concentration, to molar concentration because we don't know the molar mass of the ion tablet. So this implies that we have to first of all calculate for the CB, that's the molarity of B. That's concentration of B in mole per dm cube. For us to calculate that, we have to use the formula, the cover formula, as one of my students said, CAVA, standing for cover, over CBVB equals NA over NB, which means they're supposed to ask us first. If you can visualize II, you see there is a mix-up here. Concentration of ion 2 ion in B in mole per dm cube. This question II should come first before III. That's question III should come first. I should come first before this one that should follow up, but they mixed it up. So you find out that for you to solve I, you must know I. So I wouldn't know if it's a mistake or they're attempting the student to check their ability, because this will automatically confuse any student that is not strong. You must know the molarity of B first before you can now find the accurate mole in the volume they specified, which is this 25. So definitely I'm answering question I and I collectively. That's what I'm saying here. I'm answering this and this, because for me to get I have to solve I, which is using this cover formula. It is this formula that will be used, CAVA all over CBVB equals NA over NB. So I will tell you the volumetric analysis what formula. Okay, now let's go on. I get you understand the little, they place the cat before the dog here, so it's going to give you trouble if you don't know. So but this is what is obtainable, unless if they have mentioned the iron tablet, the molar mass of the iron tablet. We can now use the formula which says that mole per dm cube is equal to gram per dm cube all over gram per mole, meaning molar concentration is equal to mass concentration all over molar mass, such that you can now make mass concentration will be there. You make mole per dm cube, which is already what they are finding here, and then from that you can convert from the information. But here they don't. We must use CAVA to get the strength of the B in mole per dm cube. Okay, remember the concentrations in this formula must be in mole per dm cube, meaning that 10 that was given about B is not the actual concentration, because the formula here is for molarity and not for mass concentration. Okay, let's go from the question. What is Ca? Ca means concentration of acid, which was given as 0.1 times what's the volume? Va is the 17.5. That's the end point. If you are doing the real practical, you see it here. That's our Va, 17.5. Okay, then over the Cb is unknown. Don't use that 10 as your, don't use this 10 because it's in grams, and also is even in 250 and not in 1000. We'll see to that with time. Okay, so the formula here accepts only the strength in mole per dm cube times what is Vb. They told us that is 25 equals the mole ratio of the A over the mole ratio of the B. Remember that A must not stand for acid and B stand for base. They can use any letter. Don't be deceived. Okay, so because here A is standing for the oxidizing agent and B is standing for the reducing agent. So watch the A here. The Na automatically is this place. Here is only 1, but Nb is for iron, which is 5. So we have ratio of 1 is to 5. Over here is 1 is to 5. So we go down and continue our solving. So we have 1 over 5. So Cb should automatically be, after the whole calculation, remember you are going to cross multiply. Cb should imply to be 0.1 times 17.5 times 5 all over 25 times 1. So from the calculator department, what do we have as our final answer? We are going to obtain 0.1 times 17.5. Remember this is 17 times 5. Okay, 0.1 times 17.5 times 5 should be equal to 8.75. 8.75 divided by 25 is 0.35. So 8.75 divided by, so we have 8.75 divided by 25, which will give us 0.35 mole per dm cube. So this is the molarity of B. Now this, as we interpreted, remember you don't need to memorize this, you need to understand these steps I am following, because the question might come in another form. So your job is to understand what I'm solving and not to memorize it either. So the secret is on the understanding and not on the memorizing of the formula. No, just understand what I'm saying here. Remember when I taught you how to interpret this strength, I told you that 0.1 mole per dm cube, which is over here, means that it automatically implies that 0.1 is in 1000. And if 0.1 is in 1000, it also means that 1000 contains 0.1. You see how we interpreted this particular one? It's time to apply this now to solve the next question, which is this question. I've solved I. Automatically, what I have here is for question I. So this one over here, that's for this. That's the answer to this. Then we are going to now come back and solve this in real sense. So they are telling us they are asking us how many moles of iron 2 is in 25 cm cube. Well, we have gotten already that our CB is 0.35 mole per dm cube. This implies that 1 dm cube is 1000. So 1000 cm cube contains 0.35. Automatically, you ask yourself, what will 25 cm cube of the same B contain? You call it X. Following the order is going to be 1000x equal to 25 multiplied by 0.35. So making x the subject of the formula, we divide both sides by 1000. Both sides by 1000. 1000 cancels 1000, such that x will now be 25 times 0.35 all over 1000. Okay, going to the calculator department, we have that 0.35 is already waiting for us here. So we just need to know the one we are multiplying. Okay, 25 times 0.35, that's times 25 over 1000. Okay. Okay. Times 25. Okay, 0.35 times 25, then divide by 0.0078, of course. 0.00875, sorry. 0.00875. So this will give us 0.00875 moles. Remember, don't put dm cube now. If you must put per, it's going to be mole per 25 cm cube, because that's the amount in 25 this time around. So we are done with both question I and II. So because here they said the mole per dm cube, which is what I've solved. So what we just do here again, if in exam you repeat it, CA VA is equal over CB VB is equals NA over NB. What they did here is a kind of telling you fly. Then after they are finished telling you fly, they now say take wings. No, is it not when you collect your wings, you now talk of flying? There is mix up here, this and this. Okay, or less if you see otherwise, any other way we could have solved this without solving the CAVA, you can equally indicate in the comment box. Remember, make your argument constructive. See the information given about B, 10 grams. The iron tablet was not mentioned. We don't know the compound. If you know it, although we assume it's iron 2 sulfate, but don't assume until you are told. Okay, so let's go to the next question. We said concentration of iron 2 ion in B in gram per dm cube. This time around, we are looking for the concentration of the iron 2 in gram per dm cube, which is also referred to as mass concentration. Remember, we are solving 2022 GCE, WAEC GCE, alternative to practical question, the PC one. So this is what we are just using to guide you to learn how to do calculations in titration, especially in alternative to practical. Now, this is time to go back and see what the information said about B. In the beginning of the question, they told us that A is 0.100 mole per dm cube KMnO4, and also told us that B is a solution containing 10.0 grams of iron 2 tablet in 250 cm cube. So automatically we will go back and remember the fact that 250 cm cube were able to contain, according to their statement, 10.0 grams. And mass concentration is concentration in gram per dm cube. That's when we talk about grams. the type of concentration involved is automatically mass concentration. Now, concentrations are in dm cube, as you can see, not in 250 cm cube, and 1 dm cube automatically means 1000. So they are now asking us if 250 can hold 10 grams, what will 1000 gram hold? Automatically, by the multiplication factor, it should be 40, but normal mathematics calls that we have to do cross multiply such that 250x is equal to 10,000, because 1000 times 10 should be 10,000. So doing x the subject of the formula, making it the subject of the formula, we divide both sides by 250 by 250. After the long mathematics, this cancel this. 1000 divided by this automatically gives you 40 gram per dm cube. This is the answer to this question. This one, you just have to use the information given to you already in the question paper, not what you have solved previously. You know, this works step by step. What you got in I, you use it I. What you get in I, use it I. If all things being equal, what you get in IV will be probably used in the next one, which is V. What you get in V will be probably used in VI. Okay, in question V, we are told to find the percentage by mass of iron 2 in the sample of the tablet. So we, first of all, we are going to compare something. They've told us that iron is 56 gram per mole, and we are looking for iron 2 ion. This time around, we should assume that the mass of iron 2 atom is the same thing as mass of iron 2 ion. Reason is because the mass of atom and the ion do not change, because what brings about charge is the electron loss or gain, and the electron do not contribute to the mass of a particle, because the mass of electron is very negligible. It's about 1 over 1840, of course. So what I'm trying to imply here is that if the molar mass of iron atom, that's Fe, is 56, also the molar mass of iron 2 ion remains 56, because it's proton plus neutron, and the number of proton present in iron 2 atom is also the number of proton present in iron 2 ion. So do neutrons also. Is the electron that change. So now we are going to go back to the formula, which says that mole per dm cube is equal to gram per dm cube all over gram per mole. The wordings means that molarity or molar concentration is equal to mass concentration, which is concentration in gram per dm cube, all over molar mass. So for B, that's for the iron 2 sample, the B tablets, we have known everything about the iron 2 tablets, which is, we have known the mole per dm cube. Remember, in question III, which is supposed to be question II, we discovered that the mole per dm cube of the B, of the iron 2, should be 0.35 moles, while the mass concentration we got just up here is 40 grams per dm cube. So we have gotten our gram per dm cube of B is automatically 40 grams from the information they provided. Therefore, mathematically, we can now, the only thing that is unknown now remains this particular, over here, the unknown species is the unknown species remains this one. This particular gram per mole is the unknown species. Therefore, what must we do? We have to do the gram per mole subject of the formula, and that implies that gram per mole is nothing but the molar mass of B now will now be the mass concentration all over molar concentration. Mass concentration, if you do the subject of the formula over molar, therefore mass concentration is 40 over molar concentration, which is 0.35. Let's go to our calculator. We have 40 divided by 0.35. Okay, already 40 divided by 0.35. Divided by 0.35 is 114.3. So 114.3 is the molar mass, that's gram per mole per unit, is the molar mass of the whole iron 2 tablet. So to get the percentage by mass of iron, permit me to use this space here. The percentage by mass of iron 2 in the tablet, iron 2 is already 56. So we will have that 56 over total mass, which is the molar mass of the whole iron tablet. The iron tablet is, the molar mass is 114.3, and times 100 over 1. So we will have that from the calculator department, 56 over 114.3. 56 over 114.3 should be 48.99, approximately 49%, times 100 is 48.99%. So 48.99%, of which you can approximate to be 49% of the iron in the sample. So this is the answer to this question. We go to the next question. Okay, the next question should be question number 2, but it has been treated on a separate video. That should be the qualitative analysis, that's salt analysis. So we jump to number 3. You endeavor to watch that salt analysis video. This one is a random question from practical experience. It says, explain briefly why starch indicator is not added until near the end point in the titration of iodine with sodium thiosulfate solution. So you can also do yourself a favor by watching the redox titration, specifically the iodimetric titration between sodium thiosulfate and then a solution of iodine in potassium iodide here on this channel. So we got your back. We are working for your academic success. The reason is because first is to ensure accurate endpoint. To ensure accurate what endpoint, or rather you say the reason is because the starch consumes the iodine, or you say because the starch absorbs the iodine. And remember, in this titration, is required to allow the iodine present to react with the whole sodium thiosulfate. The iodine should react with the sodium thiosulfate, but if you add starch in the beginning, most of the iodine will be taken away by the starch to form a complex, which is blue-black complex. That's the presence of the color you get when iodine comes in contact with starch. So the starch is used to absorb iodine. So if you add it earlier, most of the iodine will no more react with sodium thiosulfate, leading to error in the end point. Definitely, if you add it before, towards the end, that's in the beginning or in the middle of the titration, the starch indicator, the obvious thing is that less sodium thiosulfate solution will be consumed because the iodine will be taken away from the reaction. So it leads to error in the volume of thiosulfate that is used, because the starch absorbs the iodine itself to form a complex, giving us a blue-black coloration. Okay, the next question says, drops of water were found in a bottle before filling it with an acid that was used to titrate a base solution. What effect will the drops of water have on the determination of the concentration of the base? The effect is that it will lead to wrong concentration. It will increase the concentration of the base. That's the effect. And the concentration should be the wrong one. It will increase it above normal. It will increase the concentration of the base above the real concentration, because they said we should explain or you can simply say it will lead to the error in the calculation of the concentration of the base. Then they say, explain your answer in 3bi above. That's why will you say that it will increase the concentration of the base? The reason because the presence of water in the bottle containing the acid solution will dilute the acid solution, which will result to increase in the endpoint. Result to increase in the volume of the acid consumed by the base. Because what is supposed to be is that if the strength of the base is increased, definitely it should consume more of the acid. Then invariably, if you decrease the concentration of the base, more of the volume of if you decrease the concentration of the acid, more of the volume of the acid will be used, such that we have CAVA all over CBVB. In this case, diluting the acid more will give a more, okay, I think black should be okay here. This particular VA, if you increase it, you're automatically giving chance to increase the total answer. Let's assume that we have 0.1 times 17.5 like we see previously. If you dilute the acid more, what we are going to have will be 0.1 times something like 18.5. So you have increased this the value, the VA, which automatically makes CAVA higher than CBVB, and the answer you get will be higher than normal. So that's the reason that's the possible explanation to what happens in the 3BII. Okay, we'll see question C. In that case, remember, diluting the acid will automatically lead to more of the acid being consumed. Then diluting the base will lead to less of the acid being consumed if you are titrating the acid against the base, which is always the common approach. We don't usually titrate base against acid, rather acid in the burette being poured gradually into the base. So diluting the base will lessen the endpoints, but diluting the acid will automatically increase the endpoint because more of the acid solution will be consumed. Diluting means lessening the number of moles dispersed, then increasing the water part of it. Okay, let's see the next question. Okay, over here is the next question, question C. Says a student carefully pipetted 25.0 cm cube of 0.525 mole per dm cube sodium hydroxide into a test tube and placed it in a small beaker in order to keep it from spilling. He then pipetted 75.0 cm cube of 0.355 mole per dm cube HCl into another test tube. In an attempt to put the second test tube into the second beaker, he accidentally knocks both test tubes together, thereby breaking them and their respective contents mixed up. Deduce whether the resulting solution in the beaker is acidic or basic. One might be wondering, what should I do here? Looking at the question, you need to digest it very well. First of all, you have to write the equation of the reaction. The two reactants are sodium hydroxide and then HCl. So we'll have to write and balance the equation first. We'll give you sodium chloride plus H2O is automatically balanced such that Na is 1, Nb is 1, so the mole ratio of acid to base is 1:1. So we have gotten that fact. We have to you are not going to, there is nothing unknown here. They have given us all the parameters in this formula, CAVA all over CBVB equals NA over NB. What matters here is our ability to interpret what this formula means. To explain this for you further, one should just know that CAVA over here, the implication here is that, you see this CAVA, if you multiply CAVA and divide it by the product of CBVB down here, automatically is supposed to give you the same ratio as dividing the mole of the acid to the mole of the base here. So you see, what this implies is that according to the equation we have here, we have 1:1. That's the mole ratio of the acid to the base. That means that CAVA should be equal to automatically CBVB, because 1 is equal to 1. So if we now fix in the values they gave us and discover that denominator is more than numerator or numerator is more than denominator, we will now see which one is in excess. But when they are equal, they are neutral. But from their question, they never mentioned of neutral. They asked whether it's acidic or basic. So we are likely going to see a situation whereby either the CAVA is more than the CBVB, and where CBVB is also more than CAVA. So look at our results. If CBVB is more than CAVA, it means that the solution is basic, because this is for base. That's for the sodium hydroxide. But if CAVA, the product of CAVA, is more than the product of CBVB, it automatically shows that the solution is acidic. Reason for this is because it's already established that Na is 1 and NB is also 1. Let's assume that Na is 1 and NB is let's assume that Na is 1 and NB is 2. When we multiply Ca and Va, let's assume we get something like 2. It is also applicable that when we multiply Cb and Vb, we should also get 4, because if you divide 2 over 4, it will still give you this 1 over 2. That's the implication. But in a situation where we have gotten that Na over Nb is 1 over 1, 1 over 1, it means that when CaVa gives us 2, CbVb will also give us 2, so that 2 over 2 is 1. But here, if we multiply CaVa and get something like 3, then CbVb and get something like 2, it means that there is excess acid following this particular reaction. So the mole ratio of the acid to the base is very necessary in answering this question. So let's move ahead and do the solving, because I know the solving is not actually the problem, rather this explanation, so that you can use it to answer similar questions. Remember, we are still on with Majesty Easy World Science channel. So for my explanation, we use the volumetric analysis formula CAVA over CBVB equals Na over Nb. We will now fix the values, which implies that Ca from the question, Ca is for the acid 0.355 times the volume of acid used, 75.0, all over Cb, the volume, the concentration of the base is 0.525 times the volume of the base, which is 25. If this is supposed to give us 1 over 1, from the calculator department, let's check the answer of 0. It's obvious they are not going to be the same, but let's see which one will be topping. 0. What is that? 0.355 times 75. 0.355 times 75 is equal to 26.625. 26.625. If it gives us 26.625 at the denominator and the numerator, it shows none of them is in excess. It means neutrality. But let's check that of 0.525 times 25. 0.525 times 25 This is 13.125. You see, all over 13.125. Automatically, the solution, right, for the examiner, the resulting mixture, I say the solution, the mixture is acidic. Remember, you can, if it is in practical life, you can just use your indicator, but here they are trying to give you values so that you can assess what you are expected to get when you use your indicator from the theoretical calculation. So the solution is acidic. Reason is because 26.625 is automatically more than 13.125, but the mole ratio of the acid to base is 1/1. It's supposed to, that it should be that the denominator and the numerator should be exactly the same. So the mixture is acidic, and that's the final answer. So great viewer like you, please, I beg of you, endeavor to subscribe. If you have subscribed, please stay subscribed. Subscribe, and most importantly, share my videos, not only this one. Much love from me to you. I cannot do without you. Best of luck in your exams. Majesty's World Science channel is available for you in sciences. Check out the alternative to practical videos in physics and also in biology. Bye for now.
Wait a minute, have you heard about the Majestic table? It was designed and recommended by Sir Majesty himself. Here it is. The amazing thing about the Majestic periodic table is that it provides a clear and colorful classification of elements, from P block metals to metalloids to liquid metals. It also shows the boiling and melting point of all the elements. It also has the unique feeling of electrons in the shells of each element.
Enhance the easy learning and teaching of chemistry in schools, in universities, secondary schools, in research institutes. So this Majestic periodic table, demand and special demand, as you can see that space there highlighted, that is where you can include the name of your school, or if you are dedicating it to anybody, you can write there, because you can print it to any size you like. In a Majestic size, the resolution will never be affected. So it took me about 3 months to design and provide these informations, but thank God the table is here. What made me to design this is that I discovered that these tables I see in the internet, the one I see in the market, they are not as informative as I want. And then some of them are not updated. Some still retain the fact that we have, there are like, some still see promentum has not been radioactive. Some might see them as artificial element, but it is still is a naturally occurring element, of course. So there are some modifications that this table has been made to include, and that makes it Majestic.
This is super majestic.
Much love.